Today we have our own Aaditya Ramdas talking about exponential line crossing inequalities.
So hi everyone. This talk is basically going to be about concentration inequalities. Hopefully every one of you has seen at least some basic concentration inequalities in your grad school so far. Most common ones may be Hoeffding's inequality, Bernstein's inequality, matrix versions of these. They're called Cramer-Chernoff style inequalities, things of that kind. I'm going to present some recent work that can unify all of these inequalities into a single one and can generalize and strengthen them in many ways. So this and a wide class of other inequalities all get unified. So I'll have to explain what I mean by the word strengthen as I go along in the talk, but I will let me state formally what strengthening means after I introduce the setup of the problem. Okay, so this is this title of our work is called Exponential Line Crossing Inequalities. And at a high level, it's going to be about the probability that a stochastic process crosses a line. That's why it's a line crossing inequality. And so the picture to keep in the back of your mind is where this x-axis is time, and this y-axis is a stochastic process st. So you can think about a stochastic process as being a generalization of a random walk. It's just some kind of a process that varies over time. Okay, it's just something. So the simplest one, of course, is like a sum of coin tosses, a Brownian motion, a sum of random matrices, just things of that kind, the operator norm of sum of random matrices. There's going to be some underlying stochastic process that varies over time. And we're going to ask what is the probability that it crosses a line. Okay, so that's going to be the essential underlying inequality, which is we're going to say that the probability that a stochastic process crosses is ever greater than some line is exponentially small. Okay, so that's going to be the style of the bounds. The important stuff here is going to be what is the stochastic process, what is the line, and what's the exponent. And we'll figure out how to formalize all of that soon. Now this time is not always literally time. There's something called intrinsic time, which you can think of like a variance process which captures the deviations of st. Now when st is like a sum of random variables and all of those random variables are IID, then typically intrinsic time is just time. But suppose those random variables are not IID, meaning they can have differing increments. One of them is bounded between -1 and 1, the other one's bounded between -3 and 3, and that changes. Then essentially you need another notion of the cumulative variance, which is going to be called intrinsic time. And so then Vt is not going to be just something proportional to t. It might be, it grows with time. It's non-negative and grows with time, but it's not time. It's not t. Okay, so in often in Chernoff style inequalities, we will find that Vt is just equal to t, but not always, not in general. And so that's going to be called intrinsic time. So this line that we're going to be drawing is actually going to be a line of a stochastic process against intrinsic time. Okay, there's going to be some underlying index set t, which is going to either be the natural numbers if you're talking about a discrete time process, like a sum of coin flips, or it's going to be 0 to infinity if you're talking about a continuous time process like a Brownian motion or Poisson process and so on. Okay, so you'll find that our theory applies to both kinds of processes. It's fine, it's the same statement that applies to both of them. I acknowledge that people are usually most familiar with the discrete time processes, so most of this talk will be geared towards discrete time processes because that's what maybe we are more used to seeing. And then I'll just refer you to the paper to see the stuff that's about continuous time processes because there things get interesting. You can have continuous processes with jumps, square integrable martingales. So like there's just some additional measure theory that comes in when dealing with continuous time processes. But for now, we'll keep things simple and talk about discrete time processes. So now we're going to have two processes, ST and VT. Okay, this bracket here just means I'm saying t in n in this case, but I'm going to omit saying this t in n. I'm just going to write this bracket st to refer to the entire sequence of random variables s1, s2, s2 till s infinity and v1 to v infinity. And so I'm just going to write it like this for simplicity, so that otherwise it takes me time to write it. That's what this bracket means. So if I write a bracket, I'm referring to the process. If I write a single st, I'm referring to the random variable. Okay, so we're going to have these processes st and vt, and we're going to make some assumption about these processes. Okay, so the typical assumptions that one makes with concentration inequalities are the increments of st. If it's a sum of random variables, the increments are bounded, or the increments are sub-Gaussian, or the increments are something else. We'll make usually some assumption about those increments, but we will see a more general way to write down an assumption which will allow us to derive strong concentration inequalities. Okay, and so let me state what that assumption is. And that's going to be, so this whole talk is about one assumption and one theorem. And we'll see that assumption captures most of the assumptions we typically make in the literature to prove concentration inequalities, and that theorem implies stronger versions of existing theorems, of this style. Okay, so it's just about one assumption and one theorem, and then we'll try to unpack the assumption and try to understand what the assumption really means. Okay. So we have st and vt, which are two real valued processes. Okay, so they are real valued. I'm not looking at the complex or anything of that kind, and they're going to be adapted to some underlying filtration ft, adapted to a filtration ft. Now if you're not familiar with what filtrations are, you can just think about them as a sequence of sigma fields, and according to which the original random variables are measurable. So ft is, you can think about ft as an increasing amount of information. You have more and more and more information, meaning you have larger and larger filtrations. That's just the language used when dealing with these kinds of stochastic processes. And S0 is going to be 0 and V0 is going to be 0. And this is going to be non-zero almost surely, right? It's a generalization of time, so it's also non-zero almost surely. So that's what we are given. Okay, so that's the whole problem. Every theorem, every assumption, everything we're going to state is going to be about ST and VT. Okay, so what's the assumption? The assumption is that for every lambda in some range 0 to lambda max could be infinity, there exists a super martingale I'll define what that is soon enough. I'm going to call that LT of lambda. Again, this bracket means that it's actually it's a process for all t. So it's a super martingale. And this is a super martingale with respect to this filtration Ft. So usually when you define martingales, you have to define filtrations such that expected value of L0 is a constant for all lambda. So this is just this is not that important. That's not really part of the assumption. The real assumption is that exp of lambda times st minus psi of lambda vt is less than equal to LT of lambda almost surely for all t. And when I say for all t, I mean all t in the natural numbers for this talk, but for all t in 0 to infinity if you're talking about continuous time. And where psi is just a real valued function, so psi is just real valued with domain 0 to lambda max, domain at least that. We'll talk about more properties of psi. But this is the assumption, and maybe we're going to spend a lot of time trying to understand what that assumption is saying. So let me just put it in some color so that you can see it.
So is psi a fixed function that you
Yes.
have?
Yeah.
You haven't told us what it is, but it's
Yeah, it's a fixed function. So the assumption is actually that you can find a psi. The assumption is that you can find some psi such that for every lambda, x of lambda st minus psi of lambda vt is upper bounded by a super martingale. Okay, yeah.
So what happens if we drill down and apply this to Alzweiss-Winter?
Yeah, we'll eventually get to all that. You'll get a stronger statement than Alzweiss-Winter, and I'll tell you what I mean by stronger eventually.
Okay.
Yeah, I'll tell you what st is. I'll tell you
I'm
what.
worried about stronger. I just tried to worry about how you would couch that in.
Right. So in that case,
Chernoff theorem.
st would be the operator norm of a sum of random matrices, of t random matrices. So that's what st would end up being. In that case, st will be the operator norm of a sum of random matrices. So that's the process st of the first t random matrices in the sum. And
The type of ST now would no longer be real, but would be matrices.
no, st is the operator norm of a sum of random matrices.
I see.
Of the first t random matrix. It is all real valued. Everything's real valued. There's no, so there might be an underlying process that's matrix valued, but st and vt are real
So it
valued.
would be the max eigenvalue.
Yeah,
or something.
that's the operator norm. Yep.
Okay.
Yep. Okay. So there are many ways to think about this assumption. There are, and I don't know which is the best way for you. It depends on your background. Maybe let's think about the case when st is a sum of coin flips. Okay, so this is just it's a sum of Bernoullis. St is the sum of xi's from I is equal to 1 to t. It's a sum of t coin flips, and let's say t fair coin flips. In that case, st is known to be a martingale. Okay, so we know that st is a martingale. It's a zero mean process. So what's a martingale? Maybe for those who don't know what a martingale is or a super martingale is, we say that mt is a super martingale with respect to ft if the expected value of mt plus 1 given ft is less than equal to mt, then that's the definition of a super martingale. A super martingale means the expectation goes down with time. That's what the definition means. A martingale means this is an equality. And so a sum of fair coin flips where -1 and +1 are the values of the coin flips, that is a martingale because the expected value of mt plus 1, which is the sum of the first t plus 1 coin flips, given the first t, is just the sum of the first t. Right? So that's what this statement is. That's what super martingale means. Okay, so we know that st in that case is a martingale if it was the sum of coin flips. There's a simple theorem that says that if I have a martingale and I exponentiate it, what I get is a sub-martingale. Okay, a sub-martingale is one where which the expectation increases over time. Okay, so if I take any convex function and I apply it to a martingale, I get a sub-martingale. So x of lambda times st is actually a sub-martingale. Its expectation is increasing over time. And the way to understand this is what is the function that I have to subtract from it so that it's back down to being a super martingale. I'm trying to pull it back down to it being a super martingale. So I would like to find the smallest vt, the smallest notion of variance of the process, and the smallest psi function such that I can pull it back down, and this is a super martingale. And so one example in the case of coin flips, there are many examples for coin flips. One example is where psi of lambda is lambda square by 2. Okay, it turns out that when psi of lambda is lambda square by 2 and when vt is equal to t, then that process is a super martingale for the sum of coin flips. So x of lambda sum of coin flips minus lambda square by 2 times t is a super martingale. Yeah, that's just a fact. You can verify it offline. So that's one way to understand it, is that I start with something that usually looks like a martingale. I exponentiate, I get a sub-martingale. I want to find the smallest thing I can pull it down by to get it back to being a super martingale. And so there's a tension between this term and this term. And you'll see that tension in the theorem that follows the assumption. You'll see that tension. A different way to look at this assumption is through exponential families. So maybe people in statistics are more familiar with exponential families. This left-hand side is the definition of an exponential family. It's usually defined for a single random variable. It's that, you know, the density looks like x of lambda times a sufficient statistic minus a cumulative generative function times, so it has exactly this form. If you have seen exponential families in your training, you will know that, like Bernoullis, Gaussians, Poissons, a huge set of random variables distributions are from what's called an exponential family, which means they actually have this form. And so it turns out if you take the product of these, which is the likelihood, the product of the product of the probabilities of those, the product of the densities, which is the likelihood, then it's exactly this. So it turns out that if ST, so maybe the statement is, if ST is a sum of random variables from an exponential family, then what you can prove is that the likelihood, which is x of lambda ST minus psi of lambda times t, that is a martingale. It's not just upper bounded by a super martingale, it is a martingale. The likelihood is a martingale for things from an exponential family. Okay, so that's a different way to look at it if you're familiar with exponential families. Yep.
Can you just repeat one time? So how would you define like a Poisson process from this?
Not a Poisson process. A Poisson, like the word Poisson I just said is if I have a Poisson distribution, okay, then it's a member of an exponential family.
Good. Can you define any particular one? I think I missed out on the details.
If you're not familiar with the term exponential family, then this is not the right place for me to introduce it. It takes a long time to understand what an exponential family is. And exponential family distributions are a unified way in statistics of understanding a wide class of distributions. Bernoullis, Gaussians, and Poissons are just 3 examples. There are many more, Laplace. There's lots of examples. They all have this form. It means that you can take the density of that random variable and write them in this form, where the first term is what's called a sufficient statistic. This is called the cumulative generative function.
So
and
the left-hand side, that's your definition. Oh, the left-hand side of this inequality is a definition. That's what you're saying.
Okay, the definition of an exponential family means you can write the density f of x for that random variable. It looks like, I'm just going to ignore this, there's some term called a carrier measure. It looks like e to the theta times t minus a of theta. And I'm just going to write that as f theta. There's some parameter which is often, like for a Gaussian, that would be the mean, or and so you can always write it in this form. Obviously, a Gaussian, it's very clear that you can write it in this form, but it turns out that things like Poisson and Bernoulli and many others, you can also write it in that form. And so that class of distributions is called exponential family distributions. And so if your ST was a sum of any exponential family random variables, this process on the left-hand side is a martingale. That's easy to verify. But that's if you're familiar with exponential families. If you're not, then that's not the right way to think about it. A third way to think about it is in terms of maybe what you're familiar with in terms of sub-Gaussian random variables, the definition of what a sub-Gaussian random variable is. Okay, so usually when we write the definition of a sub-Gaussian random variable, we will say that that's one definition. So what is sub-Gaussian? We say a random variable is sub-Gaussian if its moment generating function, which is e to the lambda x, is upper bounded by the moment generating function of a Gaussian. So it's e to the lambda square by 2 times sigma square. Okay, so then we say that x is sub-Gaussian if this, or x is sigma sub-Gaussian. If this holds true. Okay, completely equivalent way of writing this, the same statement is that x of lambda times x minus lambda square by 2 times sigma square is less than equal to 1. That's a completely equivalent way of writing this. So it turns out, if you start from here, then if ST is a sum of sub-Gaussian random variables, ST is a sum of such xi's, then you can take psi of lambda as lambda square by 2. You can just match this. Psi of lambda is lambda square by 2. And you can take Vt as sigma square times t, and then that process will be a super martingale. Okay, so there are essentially, you can think about this assumption as being a generalization of typical assumptions we usually make in the literature to prove concentration inequalities. This is a typical one. If you assume that these xi's are sub-Gaussian, then this assumption is true. If you assume that the xi's are coming from some parametric distribution which is an exponential family, then this assumption is true. If you assume that x is a Brownian motion, whatever, then this assumption is true. So that's just 3 examples. I'll give you more as the talk goes on. Yep.
Is there a non-trivial example which is not common in literature but satisfies your assumption?
Very, very non-trivial examples. Here's one. X is symmetric. A very interesting example. X is symmetric. Okay. Which means, what do I mean? X and minus x have the same distribution. So one example of a symmetric random variable is a Cauchy random variable. A Cauchy random variable has a density that looks like 1 by 1 plus x squared. So its tails decay polynomially and not exponentially. The Cauchy random variable is interesting because it's symmetric, but also it has no moments. Its mean does not exist. Its variance does not exist. You know, like it basically has no moments. So it does no moment generating function. So the definition of sub-Gaussian does not make sense at all. The sub-Gaussian assumption assumes that you have all moments and the moment generating function is upper bounded. I'm going to consider a random variable that is symmetric like a Cauchy that has no moments. And you can prove that basically expected value of e to the lambda x minus lambda square by 2 times x square is less than equal to 1. Okay. So note the difference between these two is that here in this case this was sigma square, which is a constant, and what ends up happening over here is that this Vt, the variance process, ends up being sigma square times t. It's a very simple process. It's deterministic and you can write it down beforehand. In this case I have x squared. What's going to end up happening over here is this Vt is the sum of xi squareds from 1 to t. It's a random quantity that you cannot write down beforehand. It's not even predictable with respect to the filtration. It's actually adapted with respect to that filtration. So this is an example. If St is a sum of symmetric random variables, then this assumption is true. Even though it's not sub-Gaussian, even though it has no moments. Yep.
Can you define Ft again?
Ft is the sigma field of S1 to St if you want. You can you have to come up with a filtration with respect to which this is true, but usually a trivial filtration is the sigma field generated by S1 to St. So that's one example, but there are more. I can write down a few other interesting ones that will probably not be known to most audiences. These are what are called self-normalized concentration inequalities or self-normalized processes. They apply even in heavy-tailed settings when you don't have moment generating functions. Okay, so here's another one. Assume only that x has 2 moments. Okay, so let's say that x has a finite variance. Okay, so it definitely cannot be sub-Gaussian. And I'm not assuming symmetry. Then you can prove that the expected value of e to the lambda times x minus lambda squared by 2 times Vt is less than equal to 1, where I'm going to just define V as 1/3 of x squared plus 2/3 of the expected value of x squared. Okay, so this is a very odd one, where the thing in there, over here it's a constant, over here it's fully random, And in this case, it's a mixture. It's a mixture of something that's fully random and something that's a constant. Okay? So it turns out that if X has finite variance, you can prove that this is true. And the implication is that this process ends up being a super martingale. That is, if I have a sum of random variables that has a finite variance only, that's the only assumption you make about the random variables, then x of lambda st minus psi of lambda vt, where vt is the 1/3 the sum of xi squareds plus 2/3 the sum of expected value of xi squareds, then that quantity will be upper bounded by a super martingale, or it will be a super martingale. So that's another non-trivial example. Yep.
Yeah, so in all of your examples so far, you've showed that this process on the left-hand side actually is a super martingale. So is there a reason for just saying that it's dominated by a super?
That's right. That's right, yeah. So all of the matrix cases, so it'll turn out that every time, so all of the cases I've talked about are scalars. If ST is a sum of random matrices, the operator norm. So, okay, so maybe I should just give you an
We're still in the hypothesis phase.
Sorry?
You haven't given us what the conclusion is.
That's right. So this is just understanding what is this assumption and why is this assumption general.
To figure out, so we don't have a theorem yet.
We don't have a theorem yet. That's right. Yeah, this is just the assumption. So essentially, in the case where you're dealing with a sum of random matrices and ST is the operator norm of the sum of the first T, this is upper bounded and not.
But it won't
be a super. It won't itself be. There's something called Lieb's theorem that's used to prove that that quantity is upper bounded by a super martingale.
So can I just ask for clarification? Let's say it's a subgaussian. Then you usually have
this one.
Yeah, let's say. Now you have the expectation of the exponential,
Yeah.
but here you don't have.
Yeah.
We haven't really said what is LT, right? We just said that
It's a super martingale. So what that means, so in this case, this quantity will be.
itself, that it's upper bound by a super martingale.
So it's in this case, what you can prove is that the expected value of exp of lambda st minus psi of lambda vt conditioned on ft minus 1 is less than equal to exp of lambda st minus 1 minus psi of lambda vt minus 1. Okay, so that's what, so in the sub-Gaussian case, you can prove that this is true. That's what it means for it to be a super martingale, is that when I take the expected value of the quantity and I condition on ft minus 1, which is one step prior, then I get it's smaller than that, and you can prove that just by peeling off one variable of the sum and applying the sub-Gaussian definition. Right? Like, because this is an exponent, if I write st as st minus 1 plus xt, and I write vt as sigma square t minus 1 plus sigma square, then the this exponential is just the product of two different exponentials. One of them just pops out because it's ft minus 1 measurable. The other one is bounded by 1. The tth term is bounded by 1. So you get that it's a super martingale. Okay, so it's two lines to prove that if you assume that the increments are sub-Gaussian, then this assumption is true. That proof is two lines. So same with every one of these other ones.
But in the matrix thing, the Lieb's theorem or whatever your fancy matrix theorem is embedded in the hypothesis. You don't prove that.
That's right.
The user has to do that.
Yes, that's right. You have to verify that in your setting this is a super martingale, and it turns out that in most of the matrix Chernoff settings, Lieb's theorem is used to basically switch the operator norm from here to a trace and so on. So there's so we can.
I just want to.
That's right. It's used to prove that Lieb's theorem is used to prove that this quantity, that this inequality really holds in the case of random matrices, where there's an operator norm over here. Lieb's theorem is used to handle that. Yeah.
If no such thing exists, then the assumption doesn't hold.
Okay, so the claim is basically that every time you're proving a Chernoff bound, you're making usually you make an assumption of the kind of the sub-Gaussian assumption. There's a more general version where you usually just assume exp of lambda times x is upper bounded by e to the psi of lambda. So that's the usual, a more general form of Cramer-Chernoff bound. This a special case is when it's sub-Gaussian, and that's just one way of making this sufficient condition true. That's just one way of making this assumption true. Basically, that is a sufficient condition for this assumption to be true. Okay, so when you usually Cramer-Chernoff bounds start by saying, assume that the xi's satisfy an equation of this kind. I'm starting by saying this is a strictly weaker assumption. Every time you make that assumption, this is also true. And this is also satisfied in cases when you don't have a sub-Gaussian kind of setting, you don't have all moments, and you have heavy tails. And if you look at the paper that was linked to the announcement, we have a big table of sufficient conditions for this assumption that hold in matrix settings, in scalar settings, in heavy tailed settings. We have a huge list of them. And pretty much almost any exponential concentration inequality that you write, which is of, I don't know, martingale style, there's something called the martingale method. Almost anything that you can prove using the martingale method, this inequality is usually embedded in there. It's a hidden assumption that nobody makes explicit often in the proofs, but it's there, and this is a strictly weaker assumption, and you get a stronger theorem from it, which is why it's worth making this weaker assumption. Okay, so does anyone have questions about the fact that the claim that this is satisfied in a wide variety of settings, and so it's a reasonable assumption to be making? I actually don't know of any setting in which you have a Chernoff style concentration inequality in which this is not true. Okay, so now let me state the theorem. Now let's assume basically you have satisfied your inequality. You have this ST, you have the process which is, let's say, a sum of random variables. You have found a psi of lambda and v such that this process is a super martingale or is upper bounded by a super martingale. You have done that. Okay, and as you can see in these three examples, psi of lambda was just lambda square by 2. But in the paper, we have many other sufficient conditions for which psi is something else. Maybe I'll just give you one. Suppose you only assume that x is lower bounded. That's the only thing that you assume. Let's say you assume that x is lower bounded by minus c. You have no other tail assumptions. You have no other moment assumptions. You have nothing else. X is upper bound is at least minus c. Then you can prove that lambda times x minus psi e of lambda is less than equal to 1, where this psi e is the cumulant generative function. It's the log mgf. It's the log mgf of the exponential distribution. Exponential distribution. Okay, so this is a different setting where this is not lambda square by 2, when I can explicitly write down what the log mgf of the exponential distribution is. I don't know if that's useful. With parameter c. So that's the c that's over there. So exponential. So this is minus log of 1 minus c lambda divided by c squared, and lambda max is 1 over c. So this is just a different setting where you can prove that essentially, if I'm taking a sum of random variables, that's in this case centered random variables, being zero mean random variables, that's lower bound by minus c, and you have no other tail assumptions about the random variable. It could have infinite variance, for example. Then, I missed x squared. I'm sorry. So, thank you. The exponential of lambda x minus psi e of lambda times x squared. So here we are again in the setting where you have a fully random variance process. And this is not lambda square by 2. It does not hold for lambda square by 2. It holds for psi e of lambda, which is this formula. So just in the paper we have 5 different psi functions, and we have looked at literature of over 50 years, and essentially there are always 5 ones that appear repeatedly: sub-Gaussian, sub-exponential, sub-Bernoulli, sub-gamma, and sub-Poisson. So even though we are making these kinds of non-parametric assumptions on the random variables, the psi functions that appear end up being the CGFs of parametric random variables. And the 5 are Bernoulli, Gaussian, exponential, gamma, and Poisson. I would say look at the paper for more such non-parametric conditions under which this assumption is true. So for now, I'll just assume you have that assumption is true, and I'll tell you what the theorem is that you can get from it. Okay, so theorem, and we'll spend some time trying to understand what that theorem is saying. Okay, so to set up the theorem, I need two transformations of psi. So you found your psi for which this is true. I'm going to call psi star the Fenchel conjugate transform. Okay, so this is the Fenchel conjugate of psi. Hopefully, it's also called the convex conjugate sometimes. Hopefully all of you know what that is, if psi and psi star is the convex conjugate or Fenchel conjugate. If you don't know what psi star is, it's fine for now. In the case of a Gaussian, if when psi is lambda square by 2, psi star of u is u square by 2. Okay, so you get lucky. If you've never heard of this before, just think of the Gaussian setting, and and as you can see, there are a lot of interesting Gaussian settings, and so psi star is u square by 2, and so if you don't know what it is, that's fine. And then I'm going to define it's a new transformation of psi, which we call the slope function. Okay, so it's a script u. It's called we call it the slope transform, and this S of u is psi of psi star prime of u divided by psi star prime of u. Okay, so this is just some transformation of psi. Once you have found your psi for which this assumption is true, you can calculate psi star and you can calculate the slope transform. In the sub-Gaussian setting, the slope transform is just u over 2. Okay, so if you're not familiar with the conjugate and so on, you can just think of psi of lambda as lambda square by 2, psi star of u as u square by 2, and S of u as u by 2. But for those of you who are more familiar with psi star, you can see you can just calculate this quantity, and I'm going to call it the slope transform. Okay, then here's the theorem. For any for any m greater than 0, and x in 0 to m b bar, where b bar is the sup over all lambda of psi prime of lambda. So b bar is the largest psi prime of lambda you can get in the domain 0 to lambda max. Often b bar is just infinity. So in the sub-Gaussian case and stuff, b bar is just infinity. So in the sub-Gaussian setting, psi prime of lambda is just lambda. Lambda max is infinity, and so this supremum is just infinity. So in the sub-Gaussian case, the x is unrestricted, but in this sub-exponential case where lambda max is 1 over c or something like that, then this b bar will be something dependent on c. Okay, so for any m and x, the probability that there exists any t, in this case in the natural numbers, but you can substitute that with 0 to infinity, where st is at least x plus s of x by m times vt minus m is less than equal to expected value of L0 times x of minus m psi star of x over m. Okay, so we'll go over this slowly. The first thing to realize is this is what I claimed it was. This is the stochastic process St. There is a line which is x plus s of x by m times vt minus m. So what is this line? So the way to imagine it is here. There's this point here which is x comma m, which is here's the level x and here's some intrinsic time m, and there is a line that is passing through x comma m, and it has slope. The slope of that line is given by this script s. That's why we call it the slope transform. Okay, so this is a line in the vt comma st plane, right? If in vt versus st plane, this is a line. It passes through the point x comma m and it has some slope. All right, so that's the line. The probability that a stochastic process crosses a line is exponentially small. So that's the way to read this. So the interesting things over here is what is the exponent and what are these other things. So what is the expected value of L0? This is just coming from the super martingale. It's simple. In the case of scalars, it's always 1. So whenever we have proved in all of our sufficient conditions in the paper, it's 1 for scalars, it's D for matrices. Okay, and if all your matrices are of low rank, then it's the rank of the lower matrices. But let's just assume they're full rank. It's basically 1 or D in the scalar or matrix case. So for now, I'm just going to forget about this term, so you can concentrate on this one. Now this term, if you've seen Cramer-Chernoff inequalities, this is a standard term that appears. The exponent is always given by the Fenchel conjugate psi star. Okay, so this form is exactly the right hand side of a Chernoff bound. It looks exactly like this. It's this left hand side that's really interesting, where now I have a bound that holds uniformly over all time. Okay, the probability, so this is a uniform bound, means that it holds like this is a simultaneous bound over all time. The probability that there exists any time at which the stochastic process ever will cross this line is exponentially small. Now usually the usual Cramer-Chernoff bound is recovered by looking at what this statement is saying at x comma m. Okay, so if I look at what this statement is saying exactly at time m only, then it just says the probability that when Vt is equal to m is what I'm saying. So basically it reduces to something of this kind, where probability that Sm is greater than or equal to x is x of minus m times psi star of x by m. Okay, so this is effectively what it's saying. So suppose Vt is just t, meaning Vt is, you're in a setting where sigma is 1, let's say it's 1 sub Gaussian, and so this Vt is just equal to t. Okay, and then in that case, if you look at what this bound is saying at time m, it's basically saying this term goes to 0, this term just cancels out, and so you just get the probability that Sm is greater than x is exponentially false. This is the Cramer-Chernoff bound. Okay, so this is the usual, in the sub-Gaussian setting, if you want to see, this is just x of minus x squared by 2m. This is what's called Hoeffding's inequality or whatever. So that's what it is. This is a more general statement for any psi that's also very well known. And so this is recovered by looking at a particular time. But now this statement is making a claim about the process uniformly over time, not just at a fixed time. Now there is an interesting theorem, a very famous theorem, some people would have heard of it. It's called Freedman's inequality. Okay, so Freedman, that's another comparison point for this theorem. So let me just mark that theorem out so you see what the theorem statement is. It's not this one below. That's the theorem statement. Okay, and another comparison point is what's called Freedman's inequality. So Freedman's inequality. So Freedman wrote a 1975 Annals of Probability paper in which he basically wanted to extend Cramer-Chernoff style inequalities. He wanted to extend them like Hoeffding's inequality to hold actually at random times as well. It will be a little hard to write down his statement in the random time setting. Random time basically means a random intrinsic time. This holds at random intrinsic times as well because it holds uniformly at all times. But one way to look at Freedman's inequality is as follows. I'm going to just write down, many of you would have seen Freedman's inequality in this way. In the sub-Gaussian setting, Freedman's inequality says it allows you to take a soup for free. The probability that at any time t less than or equal to m, st is greater than or equal to x is exponentially small. Okay, so some of you may know Hoeffding's inequality in this fashion. This is not Hoeffding's actually, but this is Freedman that proved this style of a bound. So the difference between this and this is this extra soup. This says that Sm can't be too large. This says that the max of S1, S2, S3 to Sm can't be too large. Okay, so that's this, and it's the same right hand side. Okay, so Freedman's inequality is a well-known strict generalization of Cramer-Chernoff inequalities that hold, you get a max for free without paying anything. And now this is strictly weaker than the current statement. And the way to view it is visually, is back to this graph over here. What Freedman's inequality is doing is drawing this horizontal line. Okay, and maybe I should have used a different color for Freedman's. Sorry. So this is Freedman's inequality. This is Freedman. Freedman's inequality says, I have some process ST. What is the probability that it will ever cross X before time M? Okay, so that's the way to read this. The probability that it will ever cross X but before time M. That probability is exponentially small. So our bound, maybe there's a fact that it's not obvious maybe, but I can tell you, for any of these, any other psi, for any psi, S of u is increasing in u. It's increasing in u. It's positive and increasing in u if you want. So this is really, it's a positive slope. So this, our statement is a strict generalization of Freedman's inequality. It improves Freedman's inequality before time m, because Freedman's inequality before time m is saying it will not, your stochastic process will not cross this line, and ours is saying, well, it actually won't cross this line. Okay, and it's a strict generalization after time m, because after time m Freedman's inequality says nothing, and our equality says, well, actually it will not cross this line. Okay, so this line improves Freedman's inequality in two ways, before time m and after time m. So you can think about Freedman as being this and infinity, if you want. That's the boundary of Freedman's inequality is x and then infinity, and then this boundary is strictly better. And they all recover Cramer-Chernoff at the time x comma m. So this over here is Cramer-Chernoff.
Who's this guy, Cramer?
A guy who worked on it before Chernoff. Yeah, they're called, I mean, if you look at the literature, they're also called Cramer. If you look at probability literature, they're called Cramer-Chernoff inequalities. I think Cramer was a couple of decades before Chernoff. I mean, they both did different things, but similar things, and I don't know. Hoeffding also comes into the same category. Cramer-Chernoff, Hoeffding style inequalities. They're any inequality that looks of this style, basically. Hoeffding did it maybe for the bounded random variable case, and for the Gaussian case he did it, but then you can prove more general ones when the tail is psi star and not, when the tail is psi and not lambda square. That's a generalization of Hoeffding. They're called Cramer-Chernoff inequalities. I don't know what others call them. I don't know what Anupam calls them. Maybe Chernoff bounds. What do people? Chernoff bounds. Yeah. So some people call it Chernoff bounds.
Well, I once asked Chernoff, should it be called Chernoff or Hoeffding Chernoff? He said Chernoff's fine.
Oh, when Hoeffding was
I
asked.
personally asked
I
Chernoff.
see.
I said, should it be called Hoeffding Chernoff bounds? He said, just calling it Chernoff's fine.
Okay. Well, it's the same thing. If you know what Chernoff bounds are, that's what Cramer-Chernoff bounds are. Turns out Cramer was working on large deviation inequalities.
Okay.
Like Chernoff bounds are finite sample inequalities. Cramer was looking at large deviation inequalities, which are usually asymptotic, but they were both looking at what is the right exponent that should appear, and the right exponent was often psi star. And so like that idea appeared in the asymptotic large deviation literature due to Cramer, and in the finite sample literature due to Chernoff, and so we call them Cramer-Chernoff. Fine, it's just an informal term. Okay, so that's, so any questions about this, the statement, or how to understand or read the statement?
So the curve is the same curve, independent of which of these theorems you're using, or does the curve get moved?
No, it does, because VT is different. In every one of those cases, the definition of VT is different. VT is, in this case, VT is sigma square times t. In this case, VT is the sum of xi squareds from 1 to t. In this case, the VT was 1/3 of the sum of xi squareds plus 2/3 the sum of expected value of xi squareds. And so in every case, VT is different. So, but the way to visualize it is always this.
If you put it in regular time, and then what would happen is you would just get a different curve depending upon which theorem it is?
I mean, well, if your random variables,
It's just changing the curve, right?
if your random variables are IID, okay, if your sum is IID, then VT is just t. It's the same thing. That's like, this is, or sigma square times t if it's sigma sub-Gaussian. But basically, this is equal to t if your random variables are IID, then it's fine. So I mean, that's the simple case to think about. But if you're summing random variables which have different, with different intrinsic variances, basically I can ask for a random variable, I can ask for a concentration inequality for a sum of sub-Gaussian random variables where the first one is sigma 1 sub-Gaussian, the second one is sigma 2 sub-Gaussian. I mean, I can do that, and I can get one using this bound. But so maybe for simplicity, you can think about this as just being time, and you're asking about a line. Now there's a different theorem in the self-normalized literature. If people are familiar with self-normalized concentration inequalities, there's what are called De La Pena style inequalities. So Victor De La Pena wrote a series of papers. The first one was, I think, in 1997, Annals of Probability, in which he proved concentration inequality for things like this, things like symmetric random variables. That observation was first made by De La Pena. And so he proved self-normalized concentration inequalities. What do they look like? The theorems often look like this. Probability that St divided by Vt is greater than equal to y, and Vt is greater than equal to m, is exponentially small. Okay, so they have this style, and the way to understand what a self-normalized inequality is saying, what is the purpose of self-normalization? The purpose is to handle heavy-tailed settings. In heavy-tailed settings, you have to divide St by a notion of its own variance and intrinsic variance process in order to be able to to give concentration bounds. You cannot get an absolute scale concentration for St because it might have very heavy tails. So if you want to handle settings in which it's symmetric and has really heavy tails, or it has finite variance, which still means the third moment is unbounded, or in this case again the moments might be unbounded. So if you want to handle heavy tails, you usually have to look at where you normalize the sum process by some notion of variance, and that notion of variance is usually given by the process itself. Okay, this v is not something you can define offline. Often this St will be the sum of xi's, and this Vt will be the sum of xi squareds. So that's why it's called self-normalized. You are normalizing it by itself. Okay, so these are called, so this style of inequalities. And so the way to visualize this inequality is there's Vt on the x-axis and St divided by Vt on the y-axis. And it's asking, after time m, does it ever cross level y? Okay, so that's your process. Now your process is St by Vt. That's your new process. And you're asking, after time m, does it ever cross level y? Okay, so that's the De La Pena style boundary. So it turns out that this theorem, the exact same theorem, for St divided by Vt, and you just divide by Vt on both sides to get the theorem for St divided by Vt. The boundary looks like this. And it passes through the same point over there. And that point is y comma m, or m comma y rather. And so that theorem that I wrote down, this is, our theorem, theorem 1, and this one is all De La Pena style inequalities. And there are many more in the literature after De La Pena published his work. Till 2016, 2018, people have been working on how do you prove exponential tail inequalities for heavy tail random variables. And so people have been proving self-normalized concentration inequalities. And our boundary is strictly better than the De La Pena boundary. It's better after time m because it's a lower boundary. It's better before time m because De La Pena is saying nothing and ours is giving some non-trivial bound. Okay, so it's better in both settings. And the interesting thing to see is that this is the same theorem that strengthened both Freedman's inequality and De La Pena's inequality. Freedman's inequality was trying to make a claim about the process before time m. De La Pena style inequalities are trying to make claim about the process after time m. It turns out that once you strengthen them, theorem 1 strengthens Freedman and theorem 1 strengthens De La Pena, they're the same theorem. So essentially you don't have to write a separate theorem before time m and a separate theorem after time m. You can have one theorem that applies over all time. It's a boundary that's uniform over all time that strengthens both of those style boundaries, Freedman style and De La Pena style boundaries. Okay, so that's another comparison point for this in the literature. If you want to see what it looks like and explicitly for the case of Cauchy random variables, then I like to write it in the inequality in a slightly different way because it's interesting to see. So this is the statement you can make for Cauchy's. I mean, just to unpack this in the specific case of Cauchy, you get that the sum of IID Cauchy random variables, the probability that there exists a T such that ST divided by the sum of xi squared, maybe I'll write this, the sum of xi's from I is equal to 1 to t, sum of xi squared from I is equal to 1 to t plus m is greater than or equal to x is at most e to the minus 2mx squared. Okay, so that's the statement. I don't know any other way of getting this statement. This is a new statement. Well, this theorem is new. There's this slope transform has been defined for the first time here. You can prove that this inequality can't be strengthened. This inequality actually holds with equality for Brownian motion. So we know that it can't be in general improved. And there's many other senses in which we can prove that this inequality cannot be in general improved. And we can talk about that offline. But yeah, like many of the statements you get from it are new. This is, for example, an example of a new statement. The corresponding version for sub-Gaussian random variables is where this is just sigma square times t. Okay, so that's also a new statement for sub-Gaussian random variables. If I take sum of xi's divided by sigma square times t plus m, and I ask is there ever a t at which that exceeds x, that's exponentially small, you get back Hoeffding's inequality at a particular x comma m. You can instantiate this and get back Hoeffding or Freedman and so on. And the intuition again is why you can get back those is the graph over there. But I know of no other way of proving inequalities of this style, especially in the heavy-tailed setting. In the light-tailed setting, often Freedman is fine, Hoeffding is fine, but in the heavy-tailed setting, you can get some interesting inequalities that I don't know other ways of getting. Okay, so I see that I'm out of time. Unfortunately, I didn't get time to go through many other things I would like to, but you can look at the paper for more sufficient conditions in continuous time, sufficient conditions in the matrix cases, and anytime you have something like a matrix Freedman's inequality, Tropp has a matrix Freedman's inequality. This is a strict generalization of matrix Freedman's inequality. It improves matrix Freedman's before time m and after time m. It's uniformly better than Tropp's matrix Freedman's inequality. Matrix Freedman was a generalization of the matrix Chernoff inequality, the matrix Hoeffding. So like this whole class of matrix Bernstein, all of them, every single one of them is improved by this single inequality here. So anytime you make an assumption on your matrices, you can verify that this assumption holds true. You can write down this theorem and it will be stronger than the matrix style concentration bounds that you've typically seen. And we explicitly give examples of that in the paper. It's just hard to cover a wide literature in one talk, so I will stop here since I'm out of time.